Hello, welcome to everyone in this video. This is our lecture number 2 for the theoretical part of thermodynamics. You all know already we discuss different thermodynamics problem solution, and the first lecture we discuss about zeroth law and first law of thermodynamics, and there are separate playlist for the solution of problem in the two books, that is the Thermal Physics by Roy Gupta and another book is the Thermal Physics by Garfunkel Ghosh. So if you want to watch the previous lecture and the problem solution of thermodynamics, you can go through the description box, link are given there. In this lecture we want to discuss about the second law, that is the Kelvin-Planck and the Clasius statement, and the related things, that is mainly second law. You can see the total syllabus of the BSc honors physics honors BSc physics honors for University of Calcutta. For University of Calcutta syllabus, you can see here in the first lecture we cover up this portion, that is the zeroth law and the first law of thermodynamics. Up to this portion we discuss in the first part of this lecture series. In this lecture we want to discuss this portion, that is the second law of thermodynamics, that is reversible and irreversible process with example, conversion of work into heat and heat into work, and then heat engine, then Carnot cycle, Carnot engine efficiency, refrigerator and coefficient of performance, then second law of thermodynamics, that is the Kelvin-Planck and Clausius statement and their equivalence. Up to this portion we want to cover up in this lecture, right? In the upcoming lecture we will want to cover Carnot theorem, then entropy, after that thermodynamics potential, Maxwell thermodynamics relation, Joule Thomson force plug experiment, right? And this portion already we discussed in the problem solution, kinetic theory of gas and conduction of heat problem solution we discussed in the another playlist. So in this playlist we want to discuss up to that one for this, right? So let's start today's discussion. First one, we want to know about the reversible process and irreversible process. What do we mean by reversible process? Reversible process and irreversible process. Irreversible process, right? Reversible process and irreversible process. Reversible process means the process where if you reverse the cause, then the effect also be reversed. For example, you can take a slowly isothermal process, isothermal or adiabatic isothermal process. You know, in the previous lecture, from the previous lecture, in thermodynamics process, in the PV diagram, isothermal process, the PV diagram will be like that. Okay. Slowly means you can change this is very slow process, step by step, very small step. If you change from A point to B point, and sorry, in this process, and you can go in the reverse process also, in the quasi-static process. You can say this quasi-static process. Static process. That means quasi-static process means change is very small. When the change is very small, then this can be reversible. Then you can change the cause, the effect will be also reverse. Change is very small, right? This is when the change is very small, then this is the reversal process. You can take another example. When we throw up a ball in the upward towards the gravity, it's come to the back at this position, then it can say this is the conservative force, and this process also reversible process. In the other side, that is irreversible process. So in the reversible process, you can say if we change, or if we reverse the cause, the effect also reverse. This is the reversible process. In the other side, irreversible process means if you change the cause, if we reverse the cause, the effect does not reverse. Does not reverse. That's mean if you reverse the cause, the effect does not change. For example, non-conservative force. For example, non-conservative force, that is friction force. Friction force, you can know, if you place this body at that moment, due to friction, it cannot back towards. That is the non-conservative force. And for example, you can see uh, diffusion. Diffusion, if the material comes from another person to another person, it cannot back. Or you can say heat transfer, that is the hot and this is the cold, and heat transfer through this metal or anything. Heat transfer heat transfer it cannot get back to this cold to hot, right? So this is the irreversible process. Reversible means if you change the cause, the effect also will be changed or reverse. But if you reverse the cause, the effect does not reverse. This is the irreversible process, and this is the reversible process. Clear? I think clear. Next point, we want to discuss about the work energy, work heat transformation. For that, the Joule experiment, Joule's law, you know about the Joule's law. What is Joule's law? This is nothing but W equals to JH, right? W is equals to JH, where W is work done. W is work done. This is Joule's constant. Joule's constant, whose value is 4.2 Joule per calorie, right? And this is the heat. So you can see the heat can be converted into work, or work can be converted into heat by this relation. By this relation, W equals to J. So heat can be converted into work, and work can also be converted into heat. For example, if you take a drill machine, actually this law is started from this experiment when this carpenter take this turpun, you know this turpun, the electrical version of turpun is drill machine, right? So in this turpun, you know this piano-like structure, there is a rope and this handle, take an handle, and this translate this handle, and this turpun is rotate, and this drill this portion, right? What happened when this work done? This is work done here, and due to this work done, you know at this point this produce heat. So you can see here this work done converted into heat, work done converted into heat. This is the origin of this law. And the reverse, you know, the heat can be done, work done. Suppose there is a piston and this cover up, and if you heat up you can see this displaced upward. So this displacement is nothing but work done, and this is heat. So here you can see heat can be converted into work done. Sorry. So work done can be converted into heat, and heat can be converted into work done. And this is related by this law, that is Joule's law, W equals to JH. You know all that. Okay. Now comes into the point, what is the need of second law of thermodynamics? Is the zeroth and first law is not sufficient for this discussion of thermodynamics? What is the need of second law of thermodynamics? First we know about that. What is the need of second law of thermodynamics? Second law of thermodynamics. You know from the previous lecture that the first law of thermodynamics says that is the dq d cos q, you know, state function and past function. D cos q equals to du plus dw, right? This is heat, this is internal energy, and this is work done, right? So the heat supply is used as a internal energy and work done. This is nothing but energy conservation, right? First law of thermodynamics. This is first law of thermodynamics. And this is says nothing but the energy conservation. So energy conservation will be sorry. So energy conservation so energy conservation is valid in the first law of thermodynamics, right? But here the missing, that is the flow of energy conservation. Flow of energy is does not mention here. Direction of flow, of energy is does not mention here. This is the drawback. This is the drawback of first law of thermodynamics. Okay. And this drawback removed by this second law of thermodynamics. That's why need the second law of thermodynamics. Second law of thermodynamics. Which says second law of thermodynamics, which says the direction of flow of energy or heat. Okay. For example, this is hot and this is cold. First law cannot say this heat transfer from hot to cold or cold to hot. First law does not say. But in second law, we can definitely say the flow of the heat direction. Okay. So the direction energy conservation is valid for first law of thermodynamics, but the flow of heat or flow of energy, in which direction, the direction of flow of energies does not mention clearly in the first law of thermodynamics. That's why we need to second law of thermodynamics, where discussed about the direction of flow of heat or energy, right? Clear? Here the main two there are various statements are available, but acceptable to uh, statement actually for the second law of thermodynamics, acceptable to statement are the one law, that is the acceptable to statement are Kelvin-Planck. Initially they give separate statement, but after that finally they give a combined statement, Kelvin-Planck statement, and second one is the Clasius statement. These are the two well-known or acceptable statement for the second law of thermodynamics. Okay. Before go to the second law of thermodynamics, we need to know about the Carnot engine or Carnot cycle and Carnot refrigerator. Okay. So at first we need to know about the Carnot engine. To understand the second law of thermodynamics, we need to know about the Carnot cycle or Carnot engine. uh, Carnot cycle or Carnot engine. Engine. Okay. So what is Carnot cycle or what is Carnot engine? This is the first engine developed by scientist Carnot, and then after that they are modified different part to the present engine. Okay. So this is the first engine developed by this thermodynamics. There is in this cycle there is four step. Number one, isothermal expansion. In this cycle there is four step. Then adiabatic expansion. Then isothermal compression. And finally adiabatic compression. Okay. So this is the fourth step for the Carnot cycle. If you state, if you wants to draw, the PV diagram of this fourth step, you can see here the diagram will be like that. Isothermal expansion. Suppose from here, this is isothermal expansion from A point to B point, right? After that, adiabatic expansion, so B to C. This is the adiabatic expansion. Sorry. Then isothermal compression. And after that adiabatic compression. Okay, this is D point, adiabatic compression. So this is process number 1, this is process number 2, this is process number 3, this is process number 4. And this is isothermal. Take this is at the during process temperature T1, and during this process this is temperature T2, right? So isothermal expansion, that is A to B, then adiabatic expansion B to C, then isothermal compression C to D, and adiabatic compression D to A. See, this is comes into the initial point. That's why this is called cycle, and this taken first by Carnot. So that's why this is Carnot cycle. And this behaves like an engine. What is the basic definition of engine? Engine can convert the energy into work, like that. Okay. And the basic definition of heat engine, if you want to know about the heat engine, what is the heat engine? If you know about the heat engine, the engine which converted work from heat engine, the engine which converted converted work from heat. So heat converted work is known as the heat engine, right? And in this heat engine, the special taken as the Carnot engine. And in this Carnot engine, this fourth step actually happen, or fourth cycle actually happen. If you wants to draw this in the V temperature volume diagram, you can draw during this process that this temperature is constant T1, so this will be the constant. After that, the adiabatic expansion, the volume will be like that, and after that isothermal compression like that, and then adiabatic also. So this will be the happen in the if you wants to draw in the TV diagram. This temperature is T1 and this temperature is T2, right? This is number 1, number 2, number 3 and number 4. Clear? If you wants to draw in the TV diagram of the same cycle. Okay. For this process, we want to discuss about the efficiency of this Carnot engine. About this Carnot engine. For a common engine, there is two reservoir. Temperature T1, that is called source. Temperature T2, that is called sink. There is an engine. We take the heat Q1 from temperature Q1, do some work and release some heat from towards sink. Here T1 must be greater than T2. T1 must be greater than T2. This is the called normal heat engine. Okay. For this Carnot engine, we want to discuss about the efficiency. What will be the efficiency of this Carnot engine? Okay. Let's start to find the first here the heat transfer. Actually, you can see here. This is the temperature T1 and temperature T2, and the first process will be take first step will be take isothermal. That is this is called any piston like that, and this is expand. So this will be expand and isothermal because this is temperature source is connected at T1. And the next step, if you take flow process, draw this fourth step, T1, 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 sorry, T2, T2, T2. This is first step, isothermal expansion, right? Then go to the adiabatic expansion. Adiabatic means temperature is not constant. Adiabatic expansion. Then again isothermal compression at temperature T2. So temperature T2, adiabatic compression, and then isothermal compression, and then adiabatic compression. So this is process number 1, process number 2, process number 3, process number 4. This is the 4 process of the Carnot cycle. Okay. Now comes into the efficiency. What do we mean by efficiency? Efficiency of Carnot engine. Efficiency is nothing but work done by heat supply from source, right? So from here you can see here this Q1 taken from source and W work done and Q2. So you can easily say that Q1 is nothing by W plus Q2. W plus Q2. Okay. So work done by heat supply Q1, and W equals to nothing but Q1 minus Q2. So W equals to nothing but Q1 minus Q2 by Q1. So you can easily find out in terms of Q, the efficiency will be like that. So efficiency will be 1 minus Q2 by Q1. This is the efficiency of the Carnot region. Now if you want to replace this Q1, Q2 in terms of T1, you can see here that is the Q is transfer from temperature T1 to this body is Q1, and during this process this Q is Q2. During this process Q is 0, this is Q is 0 because this is adiabatic process. So Q1, Q2 transfer only during the isothermal process, right? So you need to find out Q1 and Q2. You need to find out Q1 and Q2. What is the Q1? That is the area under this curve, isothermal process, and during the isothermal process, you know, during the isothermal process, Q1, isothermal expansion, during the isothermal process, you know, this dq equal to dw because du, which is c dv, cv dt, since this is isothermal, so dt is 0, so dq equals to dw. So this is nothing but the work done of this process, okay, which is nr t1 ln final volume minus initial volume, right? Vb by va, vb by va, vb by va. I think you remember this formula in the first lecture, the work done during the isothermal process, okay. Similarly for Q2, this is isothermal compression equal to nr. During this process, the temperature is T2 ln final minus initial. Final is D and initial is C. So d by Vc. Okay. So you got Q1, Q2. Right. So Q1 by Q2 can be related as like that. So Q1 or Q2 by Q1. So Q2 by Q1 is nothing but NR cancel out. T2 by T1 ln Vd by Vc, and this is ln Vb by Va. Okay. So this is Q2 by Q1. And this Vd by Vc and Va by Va can be related during this adiabatic process. Okay. So during adiabatic process, you know, during adiabatic process, you know this relation P V to the power gamma equal to constant. And if you changed P into T, you know PV equal to RT. So P is nothing but RT by V, V to the power gamma equal to constant. So T V to the power gamma minus 1 equal to constant, right? So if you take point B to C, point B to C for adiabatic expansion, for B to C, that is adiabatic expansion, okay. For adiabatic expansion B to C, you can see here at B temperature T1, at C temperature T2, and volume is Vb and Vc. Volume is Vb and Vc. So temperature T1, volume Vb, gamma minus 1 equals to temperature T2, volume Vc, gamma minus 1. From here you can see T1 by T2 equal to Vc by Vb, gamma minus 1. If you take this as equation number 1, sorry, equation number 2, equation number 3. For dA, for D2A, adiabatic adiabatic compression, adiabatic compression. If you go to the adiabatic compression, that is from D2A, so temperature T2 and this is temperature T1, so you can see T1 VA, T1 VA gamma minus 1 equal to T2 VD gamma minus 1. So here also T1 by T2 equals to VD by sorry, VD by VA gamma minus 1. So if you compare these 3 and 4, from 3 and 4, from 3 and 4, you can easily say that is VC by VB gamma minus 1 equals to VD by VA gamma minus 1. That is VC by VB equals to VD by VA. So you can see here that is VB by VA. So VB by VA, that is VC by VD equals to VB by VA. VC by VB equals to VB by VA. Okay. Okay. Since actually this is compression, so the work done will be minus. Volume is compressed, that is work done is minus. Okay, that's why there is a minus. So VB by VA equal to VC by VD. So if you put in this relation, there is again a minus and this is cancelled. So from 2 you can see that is Q2 by Q1. From equation 2, Q2 by Q1 equals to minus T2 by T1 ln VD by VC VD by VC, and this is VB by VA. VB by VA is VC by VD ln VC by VD. So if you reverse this, is there is a minus, so this gives us plus. So T2 by T1 ln VD by VC, and this is ln VD by VC. So finally these two are cancelled out, T2 by T1. So eta is nothing but 1 minus Q2 by Q1, that is nothing but 1 minus T2 by T1. This is the efficiency of Carnot engine in terms of temperature. This is in terms of heat and this is in terms of temperature. Efficiency of Carnot engine. Okay. T1 is the temperature of source, and T2 is the temperature of sink, and source temperature is greater than to sink. This is the Carnot cycle, and this engine is known as Carnot engine, where the heat transfer into work. Okay, where the heat transfer into work. Now go to the you can see reversible process, and after that conservation of heat into work into heat into work, heat engine, Carnot cycle, Carnot engine efficiency, refrigerator. So comes into the factor, the refrigerator comes into the topic, that is refrigerator comes into the topic, that is the refrigerator. Engine. What is engine? Is take Q1 heat from temperature T1 and do some work and eject some heat to T2 temperature C. This is the engine. Refrigerator. What is refrigerator? Actually, this is temperature T1, that is source. This is temperature T2, that is sink. Take some heat from sink. Do some work on refrigerator. Eject heat to source. This is the refrigerator. Reverse of the engine is refrigerator. Right? So you can see here, take some heat from this sink and do works on the refrigerator and eject heat to the source or high temperature. Here you remember that is T1 is greater than T2. Low temperature and this is high temperature. So cool body make cooled by doing the work done on this body. Okay. So here the parameter measure, that is the coefficient of performance. If you measure the coefficient of performance, coefficient of performance, which is denoted as omega. Here our output, that is we wants to reduce the temperature of the sink, that is the output is Q2. That means heat heat extracted from sink by the input. Here the input is work done, that is the work input. This is the definition of coefficient of performance. So this is Q2 and this is W. And you can see here that is Q1 is nothing but Q2 plus W. So W is Q1 minus Q2. So if you divide it by Q2, that is 1 minus Q1 by Q2 minus 1. And in the same reverse process, you can see this relation that is Q2 by Q1 equals to T2 by T1. Using this relation, you can see this is T1 by T2 minus 1, or this is omega, this is W. So omega is nothing but T2 by T1 minus T2. This is the omega. So what is the relation between efficiency and coefficient performance? Relation relation between efficiency and coefficient of performance. Sorry. What is the relation? You just derive this relation, that is eta equals to 1 minus T2 by T1 and omega equals to T2 by T1 minus T2. Okay. Okay. So if you divide it by T1 here, T2 by T1, 1 minus T2 by T1, and you can see here T2 by T1 is nothing but 1 minus eta. So this is 1 minus eta, this is 1 minus 1 minus eta. So 1 minus eta by 1 minus 1, that is eta. So that is 1 by eta minus 1. So 1 plus omega equals to 1 by eta. So eta equals to 1 by 1 plus omega. So this is the relation between eta and omega. Here you can see omega equals to 1 by eta minus 1, or eta equals to 1 by 1 plus omega. So this is the relation between the efficiency, that is eta, and coefficient of performance, that is omega. Okay. So there are two systems. Engine. What is engine? So basic things is engine. What is engine? Engine, we take this take the heat from source Q1 temperature, Q1 heat taken from source, do some work done and eject heat to sink. Eject heat to sink. This is engine. And the reversely, the refrigerator who take the Q2 heat from sink, do work done on this refrigerator and eject heat to this source. T1 is greater than T2. This is source and this is sink. Okay. So this is the engine and refrigerator. Clear? Sorry. So we understand the engine and refrigerator and basically find out the efficiency of the Carnot engine and the coefficient of performance of Carnot cycle. Right? Now comes into the main topic, that is the second law of thermodynamics. Second law of thermodynamics. Second law of thermodynamics. Second law of thermodynamics. Thermodynamics. Okay. Here, various scientists gives various statement for second law of thermodynamics. Mostly acceptable to statement. That is, first one is the Kelvin-Planck statement. Kelvin-Planck statement. Kelvin-Planck statement. What he says? Kelvin-Planck statement says that it says that no cyclic process, no cyclic process, no cyclic process exists that produces no other effect than the extraction of heat from a body and it conversion and it convert into an equivalent amount of mechanical work done. That's mean what he says? He says that this is temperature T1, that is source. This is sink. Sorry. This is source, this is sink. Take some heat from here and do all into work. That is, the work is Q1 and there is no to Q2. Q2 is 0. This is not possible. This Kelvin-Planck statement says we take the heat some from source and convert it into totally into work. This is not possible, right? So this is says the Kelvin-Planck statement, that is, it is impossible to take heat from the a body and convert it into totally in work. This is not possible. And you know W equals to J. So heat is converted work multiplied by this relation. So this is not taken here. Uh, you can say in the formula first law of thermodynamics, dq equals to du plus dw, right? So if du equals to 0 and that is isothermal process, you can see du equals to 0. So you can say that is dq equals to dw, q is equal to work done. So what happened here? Actually, uh, no psychokinetic process, no other effect. This is the important. Here the effect is the isothermal process. This is the state change. You remember the state change process. You think this is the important things, that is the no other effect than the extraction of heat. The other effect not possible. This is not possible without other effect. Here the other effect is the isothermal process, that is the temperature is constant. This is the effect here. That's why this is happening here. But if you take no other effect, only taking heat and converted into work, this is not possible. Okay. And second acceptable definition for the second law of thermodynamics is Clausius statement. Clausius statement. What is Clausius statement? Clausius statement says that is there exist no cyclic process, no cyclic process which has an its sole effect, total effect, sole effect the transference transference of heat from a colder to a hotter body. What he says, that is there is no cyclic process which can its whole effect transfer of heat from a colder to a hotter body. That's mean if you take this is T1 hot, that is source, this is T2, that is cold, is sink. This refrigerator take the heat Q2 and gives this Q1 equals to Q2 without no work done, W equals to 0. This is also not possible according to Clausius statement. Okay. So it is impossible to take a heat from colder body to hotter body without any work done. Without any work done, this is not possible. Sorry. Without any external work done, it is not possible to transfer heat from colder to hotter. I think clear about Clausius statement. These two statements actually accepted accepted for the second law of thermodynamics. Kelvin-Planck statement actually state about engine, and Clausius statement state about the refrigerator. Okay. Now comes into the equivalence of these two statements. Equivalence of equivalence 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 of Kelvin-Planck and Clausius statement. Clausius statement. Clausius statement. Actually, these two statements actually equivalent. We take some notation first, that is take K is represent, that is truth of the Kelvin-Planck statement. True of Kelvin-Planck statement. Okay, minus K falsity of Kelvin-Planck statement. C truth of Clasius statement. Minus C is falsity of Clasius statement. For notation. K is equivalent to C. That means Clasius statement equivalent to Kelvin-Planck statement is equivalent to Clasius statement if you can see this K imply to C or minus K imply to minus C and C implies to K or minus C implies to minus K. Either this combination true or this combination true. Okay. Either this combination or this combination true. You can see this Kelvin-Planck and Clasius statement are equivalent. So first we take that is minus C2 minus K. Same thing, minus K2 minus C. Same thing. So first take minus K implies minus C. That is false of Kelvin-Planck implies that false of Clasius. Okay. False of Kelvin. Consider a engine. Consider an engine E takes Q1 heat from hot reservoir. Takes Q1 heat from hot reservoir and does not reject any into cold reservoir. Q2 equals to 0. So this is the violation of that means it work is Q1. So this is the violation of Kelvin-Planck. That is the minus K Kelvin-Planck statement. That is the minus K. Okay. So you can say consider the engine E takes Q1 heat from source hot reservoir. Hot reservoir. Hot reservoir and reject no heat to cold reservoir, that is sink. Okay. Now if you take an refrigerator, if you take an refrigerator, this temperature T1 and T2, is take Q2 heat from the and do work done. So Q1 is nothing but W plus Q2. Okay. No violation. No violation of law. So if you take heat from sink and work done on this refrigerator and eject it to this source, this is possible, no problem. But if you combine these two things, if you combine these two things, what happen? If you combine these two things, what happen? This is engine, this is refrigerator. Take heat from here, Q1, do work, and this work converted into here. Here this Q2 equals to 0, and you can see here W equals to Q1. So if you take this Q2 and here you can see here W plus Q1 Q2, so this is Q1 plus Q2. So finally you can see here, if you take equivalent, what happen? Here take Q2 from here, refrigerator gives Q2 here. Okay, so this violate Clasius statement, so that is minus C. So we start from minus K and reach the minus C. So minus K implies minus C. Minus K implies minus C. Clear? Minus K implies minus C. So we want to just write down some note for this. So we take take refrigerator R, operate between two same reservoir and use all work done all work done to transfer it Q2 from sink to source by Q2 plus W. Okay, there is no violation of any law, no. But if we combine these two and R effectively, R if you take this as R prime, effectively this R prime takes Q2 heat from sink and without any work done on it, transfer this amount of heat sorry, without any work done on it, transfer this amount of heat to source. This violate Clausius statement. That is minus k implies minus c. So the Clausius statement, minus of Clausius statement, that is falsity of Clausius, falsity of Kelvin-Planck statement implies the falsity of Clausius statement. Clear? Now go to the another point, that is the reverse one. Minus c implies minus k. Minus c implies minus k. Go to the next one. That is minus c imply minus k. Go to the next one. Okay. So next one is says that is minus c implies minus k. What do you mean minus c? Minus c means falsity of Clausius statement. What is Clausius statement? What is Clausius statement? Falsity of Clausius statement. That means we take Q2 heat from sink and transfer this heat to source. This is the falsity of Clausius statement without only work done. W equals to 0. This is the minus C, right? Now, if you combine with this an engine, if you take an engine, which take Q1 Poriman heat, Q1 amount of heat, and do some work done on it and transfer Q2 amount of heat to this is source and this is sink, and W equals to nothing but Q1 minus Q2. No violation of law. But you combine these two things, what happen? If you just combine these two things, what happen? You can see here. This is refrigerator Q2, Q2 here, engine, take Q1, Q2, Q1 minus Q2. So, which is equivalent like that, T1 and T2, T1. Effectively, you can see this is an engine. Take here Q1 minus Q2 and this is Q1 minus Q2. That's mean total, and this is Q2 equals to 0. There is no heat transfer here. So what happened? Total heat taken from T1 converted into work done without rejecting any heat to sink. So this is minus K. So minus C implies the minus K. Minus C implies the minus K. Okay. So just write down the steps. The refrigerator, the refrigerator are transfer Q2 amount of heat from sink to source without any input work done. That means it implies, that is violation of Clasius statement, that is minus. Okay. Now taking another engine, take another engine which take heat Q1 from source and eject heat to sink by amount of Q2 with some external output work done W, which is equals to Q1 minus Q2. Here no violation of law, no problem, but the combination of refrigerator and engine gives a engine which takes Q1 minus Q2 heat from source and transferring to work done. Source and convert it totally into work done without ejecting, converted into converted totally into work done with work done ejected with any heat to sink. This violate Kelvin-Planck statement, that is minus C implies minus K. So finally we can say minus K implies minus C and minus C implies minus K. So K is equivalent to C. That is that is sorry, Kelvin-Planck and Kelvin-Planck and Clasius are equivalent. Are equivalent. So that is the equivalency of these two statements of the second law of thermodynamics. Okay, so you can see what we do today. That is the you can see here we do this portion, that is second law of thermodynamics, reversible irreversible process, conversion of work into heat and heat into work, heat engine, Carnot cycle, Carnot engine efficiency, refrigerator coefficient of performance, their relation, second law of thermodynamics, Kelvin-Planck and Clasius statement and their equivalence. Up to that portion we cover up in this portion. In the next lecture we will coming up into that portion. So that's it for today. This is all about me. This is my contact detail. You can connect with me this Telegram channel or this online platform, and this is my YouTube channel details. Go to this channel, you will get different physics related video. Like this session if you learn from this session, and share this video to your friends so that he or she also get benefit from this video. Subscribe this channel if you are new in this channel. Those already subscribed, thanks for subscription. Press the bell icon to get the notification of upcoming video. Sorry for disturbance of other sound. So thank you for listening. We'll meet in the next video as soon as possible. Thank you.